The sun feels eternal, stable, warm, perfectly sized. A golden star sitting exactly where it needs to be, close enough to keep you alive, far enough not to cook you. Everything about it feels designed for life. It isn't designed for anything. And it's slowly making Earth harder to live on. Right now, at this exact moment, the sun is getting brighter. Not dramatically, not in any way you'd notice in a lifetime or 1,000 lifetimes, but over geological time, the sun is steadily, quietly turning up the heat. Every billion years, it gets about 10% more luminous. And 10% doesn't sound like much until you run the math forward and realize what that means for the oceans, the atmosphere, and every living thing on this planet. The sun is not the perfect star for life. It's a decent one, a workable one. A star that gave us just enough time to get here and start asking questions. But out there in the galaxy, there are stars that are genuinely, measurably better. Stars that are more stable, longer-lived, gentler, and far more generous with the time they give to life. And around them, civilizations might survive for so long that humanity would look like a mayfly by comparison. Let's start with why the sun seems so good in the first place, because it genuinely is impressive. And understanding what it does well makes the problems much more interesting. The sun is a G-type star, what astronomers call a yellow dwarf. It sits almost exactly in the middle of the stellar mass range. Not too big, not too small. Its surface burns at around 5,778 Kelvin, producing a broad spectrum of light that happens to align beautifully with the peak sensitivity of the photosynthesis machinery that plants evolved on Earth. It maintains a nuclear fusion reaction in its core that has been running with remarkable consistency for about 4.6 billion years. It positioned Earth inside what we call the habitable zone, that band of distance where liquid water can exist on a planetary surface, and it kept conditions stable long enough for single-celled life to crawl out of hydrothermal vents, survive several mass extinctions, develop photosynthesis, multicellularity, nervous systems, intelligence, and eventually a species curious enough to study the star it came from. That's not nothing. That's extraordinary. But here's the thing about the sun. It's been getting better at killing us the entire time. When the sun first ignited 4.6 billion years ago, it was actually about 70% as luminous as it is today. Early Earth received significantly less solar energy, which should have made it a frozen wasteland, and yet geological evidence shows liquid water existed back then. Scientists call this the faint young sun paradox, and we still don't fully understand how Earth stayed warm enough. But the point is this: the sun was once much dimmer, Earth survived, and the sun has been brightening ever since. And it won't stop. Over the next billion years, the sun's luminosity will continue climbing. At some point, probably somewhere between 500 million and a billion years from now, that extra energy will start pushing Earth's surface temperatures beyond what photosynthesis can tolerate. Plants begin failing first. The base of the food chain collapses. CO2 levels crash as plant life dies off. The chemical balance that's maintained Earth's temperature for billions of years starts coming apart. And then the real problem begins: water. As temperatures climb, more ocean water evaporates into the atmosphere. Water vapor is itself a greenhouse gas, so more of it in the air traps more heat, which evaporates more water, which traps more heat. It's a feedback loop with only one exit, a runaway greenhouse effect, the kind Venus experienced billions of years ago when it was potentially habitable and then cooked itself into a pressure-baked hellscape of 465 degrees Celsius, where lead melts on the surface and the air weighs as much as a kilometer of ocean. Earth won't become Venus overnight. It'll take time, geological time. But the destination, if we stay around long enough, is something in that direction. The oceans evaporate. The atmosphere fills with steam. The surface temperature climbs past anything biology could tolerate. And complex life on Earth ends not because of an asteroid, not because of a supervolcano, but because our own star slowly became too much of a good thing. The Sun still has roughly 5 billion years of hydrogen left in its core, so it won't become a red giant for a long time yet. But life on Earth's surface, the window for that, may be far shorter than the Sun's lifetime. We didn't get 10 billion years. We might get 5 or 6 before it gets genuinely difficult. And complex animal life probably has 1 billion or so before conditions start becoming hostile. The universe gave us a deadline. We just don't feel it yet. So you might think, fine, what about longer-lived stars? Red dwarfs live for hundreds of billions of years. Some of them will still be burning when the universe is 10 times its current age. Surely that's the answer. Not quite. Red dwarfs, M-type stars, are the most common stars in the galaxy. They make up about 70% of all stars. They're small, cool, dim, and almost unimaginably long-lived. And in theory, that sounds perfect for life. More time means more evolution. More evolution means more complexity. More complexity means more chances for intelligence. But red dwarfs have a serious problem. Several, actually. First, they're violent in ways that yellow stars aren't. Young red dwarfs in particular are prone to enormous stellar flares. A major red dwarf flare can temporarily increase the star's X-ray output by a factor of thousands. For any planet in the habitable zone, that flare would hit like a blowtorch. Repeated flares over millions of years would strip away planetary atmospheres layer by layer. Second, any planet close enough to a red dwarf to be warm is close enough to be gravitationally locked. Tidal locking means one face permanently faces the star, roasting in permanent day. The other faces eternal night at temperatures so cold the atmosphere might freeze and fall to the ground. The dynamics of a tidally locked planet are hostile to stable, moderate climates. Third, for all their longevity, red dwarfs are dim. Photosynthesis, as we know it, might not work as efficiently under red dwarf light. Life could adapt, but it's another barrier. Red dwarfs are long-lived but volatile. Great lifespan, terrible temperament. So there's the Sun, decent lifespan, gentle enough but temporary and slowly brightening. And there are red dwarfs, eternal but violent and hostile. And sitting quietly between them, not getting nearly enough attention, are the orange dwarfs. K-type stars, orange dwarfs, are slightly smaller and cooler than the Sun and slightly larger and warmer than red dwarfs. These are, according to a growing number of astronomers, the best stars in the galaxy for life. And the more you look at the numbers, the harder that argument is to dismiss. Start with lifespan. The Sun will live for about 10 billion years total, and we're halfway through that. Orange dwarfs live for somewhere between 20 and 70 billion years, depending on mass. That's 2 to 7 times as long. The universe is only 13.8 billion years old. An orange dwarf forming today will still be burning steadily when the universe is 5 times its current age. The time it offers to life isn't just longer, it's in a completely different category. Then, look at stability. Orange dwarfs are far less prone to the violent flaring that makes red dwarfs hazardous. They're calm, consistent, and steady in energy output, which gives planets time to develop thick atmospheres and stable climates. Their habitable zones are at more comfortable distances than those of red dwarfs. Far enough that tidal locking becomes much less likely. A planet could rotate freely, with day and night cycles and seasons, and they emit less intense ultraviolet radiation than our Sun. UV is a double-edged thing for life. It drives useful chemistry in small doses, but destroys biology in large doses. Orange dwarfs sit on the gentler end of that spectrum, giving surface life a kinder environment. Alpha Centauri b is an orange dwarf in the nearest star system to Earth. Epsilon Indi, about 12 light-years away, is an orange dwarf. 61 Cygni, about 11 light-years away, is a binary pair of orange dwarfs. These aren't exotic, distant objects. They're our neighbors. Any planet in their habitable zones could, in principle, have been hosting life longer than Earth has existed, and might continue hosting it long after our sun makes Earth's surface uninhabitable. Now imagine what life looks like around one of those stars. You're on a planet roughly Earth-sized at the right distance from a steady orange sun. The sky looks different. The star is cooler and redder, so the light is warmer and more amber. Noon looks something like a permanent golden hour. Photosynthesis.